Our planet is surrounded by sempiternal space, which provides us with a chance view of equally beautiful, magnificent, and spitefully speculative sights. These extraneous scores for space support come in many sizes and shapes, but they can have a certain magnificence that can only be described poetically. Behold, the cosmic wonder is known as Einstein ring. Welcome to Z. And today, let's talk about the magnificent, uncommon, and enthralling rings of fire in outer space. The Einstein ring is one such naturally occurring phenomenon that makes space so beautiful and intriguing. Though such cosmic oddity may deceive you with its supernatural glamour like every other thing in our universe, there is well-defined science behind their existence. In fact, we theorize their existence. The universe frequently surprises us with naturally occurring phenomena that may put our highly imaginative fantasies to shame. The Einstein ring is a phenomenon that occurs when light from far-off objects, such as galaxies, stars, and nebulas, passes through an extremely large mass, such as a galaxy cluster. The light from the background galaxy is diverted and distorted around the massive intervening cluster, forcing it to travel along many different light paths toward Earth and giving the impression that the galaxy is in multiple locations at once. A few years before he published his theory of general relativity in 1916, Einstein foresaw the bending of light by a gravitational substance in 1912. The ring effect was first mentioned in the academic literature by Orest Valsen in a brief article in 1924, in which he mentioned the halo effect of gravitation when the source lens and observer are in nearly perfect alignment. However, the effect was confirmed by the British astronomer Arthur Eddington in 1919 during a solar eclipse on the island of Príncipe. At the time, we didn't have telescopes powerful enough to detect signs of this phenomenon. In 1936, Einstein made a remark about this phenomenon. He proposed that the fabric of space-time was not rigid but flexible like the surface of a trampoline. A massive object, in this case a foreground galaxy, can bend space the way a bowling ball bends the fabric of the trampoline. This bend causes any light from background objects to curve around the foreground object instead of traveling in a straight line. If the two objects are perfectly lined up, the background object will be in. In one of its most recent findings, NASA's Hubble telescope found a distant galaxy that is approximately 9.4 billion light-years away from us yet is considerably magnified and deformed by the forces of gravitationally twisted space. This galaxy, which is at the pinnacle of star creation and cosmic development, is an example of one of the largest nearly complete Einstein rings ever seen. Hubble was able to capture the lensing effect as it also created multiple apparitions around the curved arc of the single background magnified galaxy because the stars in the concerned galaxy were born at a rate 1,000 times faster than within our own. As a result of this boost by Mother Nature, the galaxy's light was magnified by a factor of 20. In the course of our space exploration, we have encountered hundreds of gravitational lenses, about half of which are partial Einstein rings with diameters up to an arc-second, even though either the mass distribution of the lenses is not perfectly axially symmetrical or the source lens and observer are not perfectly aligned. For these reasons, finding a perfect Einstein ring is such a significant achievement. Hubble imaging was required to accurately simulate the lensing's effects on the galaxy's appearance in order to determine the galaxy's physical characteristics. Hubble was instrumental in identifying the lens galaxies for replicated images and star clumps. Because of its location in the southern hemisphere constellation of Fornax, sometimes known as the Furnace, and its clumped appearance, the ring, codenamed Gal-Clos 022058S, may have been fittingly named the Molten Ring. The round object in the center of the image, which was released by the European Space Agency, ESA, is actually 3 galaxies that appear to be 7. The image is a combination of 4 separate images of the most distant galaxies, which form the ring around the other galaxies. Last year, Hubble was able to capture yet another perfect Einstein ring, this one located about 3.4 billion light-years from Earth and forming a visible ring. Given that the farthest galaxy is billions of light-years away from us and has a massive black hole at its center, it should be invisible to even the best telescopes. However, because the light from the galaxy is bent by the 2 galaxies in front, which are about 3 billion light-years away, the image of the galaxy appears 5 times, 4 times on the ring and once on the other 2. In contrast to gravitationally lensed light sources, which are typically shaped into Einstein rings due to the elongated shape of the lensing galaxy and the quasar being off-center, such formation is frequently thought of as an Einstein cross, a variant of the Einstein ring, and is quite frequently found among most of the discovered Einstein rings. The extent of the amplified X-ray generating zone encircling the far-off black hole, estimated to have the mass of 500 million suns, has been measured using data from NASA's Chandra X-ray Observatory. A team of academics has discovered that the black hole responsible for Einstein's cross is spinning unbelievably mind-bogglingly fast, over 70% of the speed of light, or around 470 million miles per hour, using a technique called microlensing that magnifies individual stars in the intervening galaxy. These results show that supermassive black holes like the one in Einstein's cross can continue to accelerate for billions of years after gathering matter into rapidly spinning multi-million-degree disks, especially when they are lined up with their own rotation. The existence of Einstein rings must satisfy 2 conditions. Although such a geometric arrangement is highly unlikely for point-like sources because astrophysical sources in the real universe have a finite extent, it is sufficient if a portion of the source covers the point caustic in order to produce such an annular image that was slightly off-center. The mass distribution of the lens needs to be roughly axially symmetric as seen from the observer, and the source must lie exactly on top of the resulting degenerate point-like caustic. The first Einstein ring was found in 1988 when a quasar was lensed by a nearby galaxy into 2 very similar images of the same object. These images were stretched around the lens into an almost complete ring. It took us another 10 years to find the first complete Einstein ring. The galaxy that caused the lens here is an old elliptical galaxy, and the image we were able to see through the lens is a dark dwarf satellite galaxy that we would not be able to see otherwise because we observed multiple rings around it. The molten ring is such an impactful discovery. The odds of finding a double ring around a massive galaxy are 1 in 10,000, making molten rings such a rare find. It's like discovering a hidden treasure. Einstein rings help us to understand deep space better than our capabilities. They reveal more information about the distribution of dark matter and dark energy, the nature of distant galaxies, and the curvature of the universe. Comment below with any information you believe we could learn from these ancient galaxies that are out of our reach. As always, thanks for watching Z.